Hello friends, in this video let us derive the transfer function for DC servo motor which is field control. So let us understand initially what is a servo motor. So servo motor is nothing but any electrical motor when it is operated with the help of servo mechanism, then that electrical motor is referred as the servo motor. So a simple electrical motor when it is operated with the servo mechanism gives you the servo motor. So if the motor as a control device associated with your servo mechanism is DC motor, that is DC plus servo mechanism gives you DC servo motor, and if the electrical motor as a control device associated with the servo mechanism is your AC motor, then it gives you AC servo motor. So generally the servo motors are used for positioning control systems in robotics, in toy cars, in compact discs as you have seen, and in processing tools. So let us briefly see what is the working of the servo mechanism, that is the working of the DC servo motor with the help of this servo mechanism. So the servo mechanism employs some special purpose components. So one is the potentiometer, and other is the gearbox, and other is the intelligent circuitry. So your DC motor along with these special purpose components is referred as the DC servo motor. So DC servo motor is nothing but the DC motor when it is active with the special purpose components, the potentiometer, gearbox and intelligent circuitry, then it is referred as the DC servo motor. Now let us say I am having a DC motor here, a simple electrical DC motor. The output and the shaft I am taking from the DC motor, and it is connected to the gearbox for speed reduction. So the gearbox reduces the high speed into the normal speed, which are generally used for practical applications, and from here I am having a position cog. and from here I am having the shaft output. The position cog function is it transfers the motion of the shaft onto some other wheel. So here I am having a potentiometer, and from the potentiometer I am generating an electrical signal which is fed to a error detecting amplifier, and here I am having one other more signal, that is a reference input electrical signal, and the third signal is fed to your DC motor. So this is the cog, this is your potentiometer, and this is your error detecting amplifier, and here is your feedback loop. This is your feedback loop, and now the potentiometer knob is coupled to the shaft of your DC motor. Now as the shaft rotates, the knob of the potentiometer also rotates, and there will be an electrical signal generated at the potentiometer output port, and which is fed to the error detecting amplifier, and again we are already having the reference input electrical signal. The difference of these two signals is compared in your error detecting amplifier, and the difference is amplified, that is compared and amplified and fed to your DC motor for adjusting the shaft position of the shaft output. Now once the difference of these two signals becomes zero, then there won't be any third signal generated, and the motor will come to stop state, that is an off state, or you can say the motor stops rotating. So now until you get the desired position of the shaft output, there will always be an electrical signal generated from the potentiometer output. So once you get the desired position of the shaft, then automatically the potentiometer output signal, that is from the potentiometer output port, will be automatically gets equal to the reference input signal fed to the error detecting amplifier, and the motor stops rotating. So this is the basic working principle of your DC servo motor, how it works with the special purpose components, the potentiometer and the gearbox, and with the intelligent control circuitry. So let us now move to the transfer function of the field control DC servo motor. So let us see the schematic diagram of the field control DC servo. So this side here I am having the amplified error signal or you can say the input applied voltage EF, and IF is the field current, it is RF, which is the field winding resistance, which is LF, field winding inductance. So from these two ports I am having the applied input voltage, there is a field applied input voltage, and this side I am having, it is the armature current, and this is my armature, where Tm is a torque developed by motor, and J comma F naught are the mechanical parameters, where J is referred as the equivalent moment of inertia referred to the motor shaft, and F naught is the equivalent viscous friction coefficient referred to the motor shaft. And for the motor to be utilized as for a DC motor to be utilized as a DC servo motor, it requires two separate DC sources, one for the field circuit and one for the armature circuit. So here we are having one servo amplifier from which we are getting amplified error signal, and here we are having a constant current source, so where the IA is constant for your field control DC servo motor. Now, looking to the BH curve or the magnetization curve for your field control DC servo motor, so here I am saying the air gap flux phi, and this is my excited current IF. So then the characteristics will be like this. So here is your knee point. So beyond knee point, these characteristics will be used for your armature control, because in armature control the flux is kept constant. So beyond knee point, the field circuit goes to saturation, and therefore the flux will remain almost constant. But in the field control DC servo motor, we are going to operate in the linear range of the magnetization curve. So we are going to operate in the linear range of magnetization curve, because in a field control DC servo motor, the flux has to vary as you vary the field current. So for the linear range of magnetization curve, I can write the phi is proportional to IF. So as phi is proportional to IF, I can write, removing the proportional design, phi is equal to KF into IF. So I know from the general motor torque equation for the DC motor, it will be given by torque is proportional to the product of phi and the armature current IA. So plugging phi is equal to K phi IA here, your torque is proportional to KF IF into IA. So removing the proportional sign, I am writing a constant K1 KF IA into IF. So in the field control DC servo motor, the armature current is kept constant. That means the motor shaft output, that is the angular displacement of the motor shaft output, is controlled by the applied field input voltage, but the armature current is kept constant. So I am writing is T is equal to some KT into IF. KT is the motor torque constant. So this is your torque equation for the motor. Now let us apply KVL in this loop. Now applying KVL in this loop, I will get E of F will be equal to IF RF plus LF into DIF by dt. So this is one equation and this is the other equation. Now we are having two mechanical parameters J and F naught. So therefore the mechanical torque will be given by J into d squared theta upon dt plus F naught into d theta upon dt. So this torque will be equal to your electrical torque. So I am equalizing them, then it will be equal to J into d squared theta upon dt plus F naught into d theta upon dt. So this is your third equation. Now the transfer function is nothing but the Laplace of the output, where theta is your output. So Laplace of the output theta s upon the Laplace of the input EF of s is your transfer function for the field control DC servo motor. Therefore, let us convert the differential equation into the Laplace domain. So by converting it into the Laplace domain, let us write EF of s will be equal to RF plus s into LF into if of s. So this is one Laplace equation, and from here t of s will be equal to kt into if of s. It will be equal to js square plus f naught s into theta of s. So from these two Laplace equations, let us form an overall block diagram for the field control DC servo. So here I know the EF is the input, that means for the first block the input signal should be EF. So for the first block the input signal is EF. So from here I can write EF upon EF of S is equal to 1 upon RF plus S into LF. So this is one block. So here it should be IF of S, and here it should be EF of S. So this is your EF of S, and here you are having 1 upon RF plus S into LF. So this is 1 upon RF plus S into LF. So from here I am having again IF of S, that is T of S upon IF of S will be equal to KT. So this will be my KT block, and the output is T of S. Output is T of S, and from this equation the theta of S upon T of S will be given by 1 upon J square plus F naught S. So the output is theta of S, and the block here it is 1 upon J square plus F naught S. So this is your KT. Now either by block diagram reduction technique or by adjusting these equations we can find the overall, that is we can find the transfer function for your field control DC servo motor. So the theta S upon EF of S will be given by simply block diagram reduction technique. As this is a open loop transfer function, we can multiply all the three transfer functions. This is one transfer function, or this is the other transfer function, and this is the other transfer function. By multiplying the three transfer functions we will get the complete, or we can say the overall transfer function for your DC servo motor. So the transfer function for your DC servo motor will be KT upon, if I take S common, so Sj plus F naught, it will be RF plus S into LF. Now I know the angular velocity of the shaft omega is given by the d theta upon dt. So from here I can write omega is equal to S into theta of S. So if I multiply here S, so then it will become omega of S into theta of S will be equal to omega of S. Then the Laplace, the transfer function will be equal to the Laplace of the angular velocity, that is the Laplace of the angular velocity to the Laplace of the input field voltage. So here if I take my F naught common from this term and RF common from this term, then I'll get theta of S upon EF of S, and writing it in more generalized transfer function form, it will be equal to Km upon S into S tau m plus S into S tau m plus 1 plus S into tau f plus 1. So where Km is the motor gain constant and tau m is the mechanical time constant and tau f is the field winding time constant. So where Km, your Km will be given by, so if I write here, where Km will be given by Kt upon Rf into J. So this is your mechanical, that is the motor gain constant, and tau m is given by, that is a mechanical time constant, it is J by F naught, and tau f is a field winding time constant, it is given by Lf by Rf. So this is a transfer function for your field control DC servo motor. Now if you observe the field, that is the armature control DC motor transfer function, So it will be theta s upon Ea of s, it will be equal to Km upon s into s tau m plus 1. So this is the transfer function for your armature control DC servo motor, where we are having a single, this is the tau m is the motor time constant, where we are having a single time constant. That's why this transfer function, the transfer function of the armature control DC servo motor is also called as a single time constant function. And here we are having two time constants, one is the mechanical time constant and the other one is the field time constant. So here we are considering the armature inductance to be 0. So therefore you can say the open loop transfer function of the field control DC servo motor has two time constants, and the closed loop transfer function of your armature control DC servo motor has a single time constant, as the armature that is the armature inductance can be considered to be 0. So the advantage of your field control DC servo motor is as the power, or you can say as the motor is controlled by the field circuit, therefore the controlling power requirement is very small compared to the rated power. So since the field circuit is controlling the DC motor, so therefore the controlling power requirement is smaller than the rated power of the motor. But the disadvantage is, now since the field circuit is in inductive in nature, it has slower dynamic response for the applied input error signal. Slower dynamic response due to the inductive nature, it is having a long time constant. So now the field circuit is an electromagnet which is inductive in nature, and due to sudden change in the applied input error signal, there is a high rise, or you can say there is a rise in the field current to a steady state value depending on the time period of the inductive circuit, or you can say the time constant of the inductive circuit, the current will rise to a steady state value. So due to this slower dynamic response, the field controlled DC servo motor arrangement is only used in small motors. So due to the inductive nature of the field circuit, which is having a slower dynamic response, therefore it is used in small motors only. And the other disadvantage is, here we do not have the role of the back EMF. So in the field control DC motors, generally the field control is done beyond the rated speed. So beyond the rated speed, there will be a very small change in the speed. So we know the back EMF will be proportional to d theta upon dt. So since the change is very small, because the field control is done after the rated speed of the motor, and after the rated speed, the speed change is very small, and since the speed change is very small, and as the EEB is proportional to d theta upon dt, you can consider your EEB to be approximately 0. So therefore, the back EMF doesn't contribute the additional damping. It doesn't contribute the additional damping over and above the load friction. So in armature control DC servo motors, there is a effective back EMF, and which provides the additional damping over and above the load friction. But here we do not have the additional back EMF, as the field control is done above the rated speed. So this is the other disadvantage. So here we have written it is J. It is not J. It is F0, as we have taken F0 common from here. So it is RF into F0. So this is all about the transfer function of your DC servo motor. I hope you understood well. Please subscribe to the channel. Thank you.